is arriving before the refraction from that thin layer all the time. So the thin layer is actually later in time than both the direct wave and the first refraction. And so because it's later in time, it's messed up with a lot of other arrivals that are going on there, and we're not able to estimate it in many cases. The only thing that we're really doing in refraction seismic is measuring that first arrival. So in this case, the thin layer isn't a first arrival, and we might not see it. We probably won't see it. Here's one other issue. What if we have lateral velocity changes? We know the Earth is not homogeneous. Well, in this case, we're going to get a different slope for the two arrivals. And that's how we can often tell that we're looking at a lateral velocity change. But notice that this thing will look, in some ways, like a dipping layer. Okay, I'm going to go over this part, what's called the plus-minus method of interpreting refraction seismic next time. But what I'd like to do now is go into the next section, the surface wave section. Okay, so what we've seen is that for refraction seismic, this is a problem. Like characterizing low velocity layers underneath high velocity layers is impossible to do because it doesn't get refracted. So refraction seismic's great for estimating bedrock, but it might not be so good for estimating zones that are weak, that have liquefaction potential, that are basically less consolidated underneath more consolidated. The example that we talked about, if this exists, is permafrost here. Going into rock that is not filled with ice. You got it, Noah? So what we're going to do now is we're going to talk about Rayleigh waves. And I'm going to just give you kind of the Reader's Digest summary of this right now. So the first thing we know about Rayleigh waves is that they travel near the surface. They actually travel in a zone like this. They basically propagate along the surface, but in a zone that's dictated by the wavelength. So the amplitude at the surface of the Rayleigh wave is big, and as we go away from the surface, the amplitude of the Rayleigh wave drops. And it drops as the wavelength which means to say that, actually no, sorry, one over the wavelength. Which is to say that for a fixed z, if the wavelength is really large, this exponential approaches 1. It doesn't drop very quickly with z. If the wavelength is small, the wave drops quickly. We'll go over that in more detail essentially what it means is that long wavelengths penetrate deeper in the earth than short wavelengths. Long wavelengths are longer. Now, what does that say about frequencies? What's the relationship between wavelength and frequency? V is F lambda, right? So lambda, so F is going to be V over lambda. So the longer wavelengths are going to have lower frequencies. Shorter wavelengths are going to have higher frequencies. So what this means is that lower frequencies are going to travel deeper into the ground than higher frequencies. And we're going to use this to our advantage because we're basically going to look at the Rayleigh wave speed as a function of frequency. So we know from that argument, e to the minus z over lambda, we know that if lambda is high, which means that the frequency is high, or sorry, lambda is low, short. The frequency is high, that the wave is going to travel in the near surface. If the wavelength is large, and the frequency is low, then the wavelength is basically going to travel C, a deeper section of the Earth in the short wave. So if we could generate, and remember that these arrivals are basically traveling with the velocity of the Rayleigh wave. Okay. And it turns out that the velocity of the Rayleigh wave is about 0.94 the shear wave velocity. So if we could measure the velocity of the Rayleigh wave as a function of frequency, if we could send different frequency waves into the ground. The first tone is a C, the next tone is a B, the next tone is an A. Going down, we're seeing different depths in the Earth. Everybody understand that? Is that totally totally agree? Not surprised. It's kind of a tricky concept. Let me see if I can explain it another way. A frequency of, let's say, 15 hertz might investigate a depth zone of 3 meters. A frequency of 5 hertz might investigate a depth zone of 20 meters. So again, if you can get V Rayleigh as a function of frequency, you can convert that to V shear as a function of depth. True techniques that we'll be looking at. That's pretty cool. All you have to do is make these Rayleigh wave velocity measurements at different frequencies, and you get shear wave as a function of depth through some magic machination. Now the cool thing about the Rayleigh wave is that it's a travels horizontally. So it's like a direct wave in that respect. So all the travel time inversion techniques can into the direct wave. Okay, so this is a general expression for the Rayleigh wave. Start out with initial source amplitude A. It drops as the offset to the square root. Why is that? Why does the Rayleigh wave drop in amplitude as the square root of x? Yeah, it's basically propagating in 2 dimensions, not in 3 dimensions. Trapped through the surface. Here is the depth dependence. And then there's basically the Rayleigh wave velocity, which is 0.92, 0.94. It's basically a fraction of beta. And that fraction doesn't vary too much. So this basically summarized what I talked about. As lambda increases, the depth of penetration of the Rayleigh wave increases. Because the shear wave velocity increases,